This is the story of a line that does not exist, and of the people who have spent 70 years arguing about exactly where to draw it anyway. Space does not begin at a wall, a fence, or a visible seam in the sky, and depending on which government agency, which international federation, or which billionaire you ask, the edge of space sits somewhere between 80 and 100 kilometers above your head, with real consequences for who gets to call themselves an astronaut. If you've ever wondered why two men who flew to almost the same altitude in the same summer got treated completely differently by history, stick around, because that story is coming, and it says more about human nature than it does about physics. Before we get into it, if you're the kind of person who likes finding out that the universe is stranger and messier than you were taught in school, go ahead and hit subscribe, drop a like on your way out, and let's get into where space actually begins. Here is the part that surprises most people first. There is no edge. Not a physical one, anyway. Earth's atmosphere does not stop the way a swimming pool stops at the tile, with air on one side and vacuum on the other. It thins out, gradually, molecule by molecule, getting less and less dense the higher you climb, until eventually there are so few particles left that the difference between atmosphere and empty space becomes a matter of definition rather than a matter of fact. Even at 400 kilometers, where the International Space Station orbits, there is still enough atmosphere left to create drag, enough to slowly pull the station's orbit downward every single day, which means engineers have to periodically reboost it using the engines of resupply spacecraft just to keep it from sinking. And if there's still measurable atmosphere at 400 kilometers, tugging at a station the size of a football field, you can start to see the problem with picking any single number and calling it the edge. So why does the number 100 kilometers get repeated so often? Why do so many headlines, so many textbooks, and so many space tourism companies treat 100 kilometers as though it were etched into the fabric of the universe? The answer starts with a Hungarian-American physicist named Theodor von Karman, and it is a story about how a rough back-of-the-envelope calculation from the 1950s somehow became the most quoted number in modern spaceflight. Von Karman was born in Budapest in 1881, recognized as a mathematical prodigy by the age of 6, and he moved to the United States in 1930, where he built and led the Guggenheim Aeronautical Laboratory at Caltech. That laboratory eventually evolved into what we now know as NASA's Jet Propulsion Laboratory, which tells you something about the caliber of thinking this man was capable of. By the time he turned his attention to the edge of the atmosphere in the 1950s, von Karman had already spent decades earning a reputation as, among other things, the father of supersonic flight. He developed foundational mathematics for studying airflow at speeds faster than sound, work that directly underpins the design of every supersonic aircraft built since. He co-founded the Aerojet General Corporation in 1941 to build early American rocket engines, and in 1945, working with his graduate student Frank Molina, he helped launch the WAC Corporal, the first American-sounding rocket to reach genuinely high altitude. Fluid dynamics students still learn his name today through something called the Karman vortex street, the alternating pattern of swirling eddies that peels off behind any blunt object moving through a fluid, from a bridge pylon in a river to a stalled aircraft wing in flight. He died in Aachen, Germany, in 1963, and is buried in Pasadena, not far from the laboratory he helped found, and a crater on Mars now carries his name. In the mid-1950s, well before Sputnik, well before any human had left the ground in a spacecraft, this same man sat down to work out a very specific engineering question. At what altitude does an airplane's wings simply stop working? Not because the plane is broken, but because the air itself becomes too thin to generate lift, no matter how fast you're flying. He reasoned that there had to be a crossover point, an altitude where a wing would need to travel at orbital velocity, roughly 8 kilometers per second, just to generate enough lift to stay airborne in the ever-thinning air. Past that point, you're not really flying anymore in any conventional sense. You're just barely staying up because you're going so fast that momentum is doing the work gravity would otherwise be undoing. When von Karman ran the numbers, he landed on a figure of approximately 83.8 kilometers, or 52 miles. Not 100, 84, roughly. That's the actual result of his calculation, and it's worth sitting with for a second. because it means the number most people repeat when they talk about the Kármán line isn't actually the number Kármán calculated. A colleague of his, the space lawyer Andrew G. Haley, later proposed using von Kármán's altitude as a formal legal and aeronautical boundary between airspace and outer space, and it was Haley who put von Kármán's name on it. The organization that eventually adopted that number, the Fédération Aéronautique Internationale, is worth knowing a little about, because it long predates the space age entirely. It traces back to June 10, 1905, when a trio of European aviation enthusiasts pitched the Olympic Congress in Brussels on the idea of a single international body to standardize and certify aviation achievements. At a moment when pioneers like the Wright brothers and Alberto Santos Dumont were still proving that powered flight was even possible in the first place. That proposal turned into a formal conference in Paris that October, and on October 14, 1905, delegates from Belgium, France, Germany, Great Britain, Italy, Spain, Switzerland, and the United States formally founded the organization, with the explicit mission of cataloging the best aviation performances in the world so record claims could be compared and verified fairly. For half a century, it concerned itself entirely with airplanes, balloons, and gliders. It wasn't until the dawn of actual spaceflight, decades later, that the same organization found itself in the business of deciding, essentially by committee vote, where the sky stops counting as sky. So when the Fédération Aéronautique Internationale sat down to formalize von Kármán's number around 1960, they rounded it up. Not because new physics justified a higher number, but because, according to space law expert Thomas Gungale and astrophysicist Jonathan McDowell, 100 kilometers is simply easier to remember than 84. It fits better on a certificate. And so the world inherited a boundary that was, in its final form, adjusted upward for reasons that had more to do with aesthetics than aerodynamics. That's not really a knock on the FAI. Somebody had to pick a number, and record-keeping organizations need a consistent standard to compare one flight against another. But it's worth knowing that the most famous line in spaceflight was nudged upward by roughly 16 kilometers, largely because a rounder figure was easier to remember. And here's where it gets more interesting, because the United States never actually adopted that 100-kilometer figure. While the rest of the world was settling on the FAI's rounded number, NASA, the United States Air Force, and later the Federal Aviation Administration all quietly went a different direction. They set their own boundary at 50 miles, which converts to roughly 80 kilometers. That's strange when you first hear it, until you realize 80 kilometers is actually closer to von Kármán's original, unrounded calculation than the FAI's own 100-kilometer line is. The country that didn't name the line after the man ended up using a number closer to his real math than the country that did. This split matters, because it produced two separate American definitions of spaceflight running side by side for decades, and the story of how that split played out is one of the quietly unfair chapters in the history of American aviation. Between 1959 and 1968, a rocket-powered aircraft called the North American X-15 flew a combined 199 flights, piloted by 12 different men. The X-15 wasn't launched from the ground like a rocket. It was carried aloft under the wing of a mothership aircraft and released at high altitude, at which point its rocket engine would ignite and blast it upward on a ballistic arc, high enough that for a few minutes at a time, a pilot in an airplane was also, technically, an astronaut. 8 of those 12 pilots flew a combined 13 flights that cleared the 50-mile, 80-kilometer threshold the US Air Force used to define spaceflight. Of those 13 flights, only 2, both flown by the same civilian pilot, also cleared the FAI's stricter 100-kilometer line. Now here's the part that stings. 5 of the pilots who crossed 50 miles were active-duty Air Force officers: Robert White, Robert Rushworth, Joe Engel, William Pete Knight, and Michael J. Adams. Because they were military personnel, the Air Force immediately recognized them and awarded them astronaut wings. The other 3 pilots who flew just as high, and in one case higher, were NASA civilians: Joe Walker, John Jack McKay, and William Bill Dana. Because NASA policy at the time didn't provide a mechanism for awarding astronaut wings to test pilots, these 3 men received nothing: no pin, no ceremony. No official acknowledgement that they had done exactly what their military counterparts had done, and had done it to get there. Robert White became the first X-15 pilot to break 50 miles back in 1961, eventually pushing the aircraft to Mach 6.04, the fastest speed ever achieved in a piloted winged aircraft up to that point. Joe Engle flew his qualifying mission on June 29, 1965, becoming the youngest person to ever earn astronaut wings at the time. But it's Joe Walker's story that really shows the absurdity of the whole arrangement. In July and August of 1963, Walker flew above 100 kilometers twice, becoming the first human being to cross the FAI's own strict boundary in a winged aircraft. His unofficial altitude record from that summer, 354,200 feet, or 67 miles, stood for more than 40 years, until Scaled Composites' Spaceship One finally broke it in 2004. Walker had, by any reasonable definition, gone to space, and gone there more decisively than most of the men who did receive astronaut wings that year. And still, because of a technicality about who signed his paycheck, he got nothing, not for another 4 decades. Not one of the X-15 flights was without danger. Neil Armstrong himself flew the X-15 before he was selected for astronaut training, and on April 20, 1962, during what became the longest X-15 flight in the program's history at 12 minutes and 28 seconds, he pulled up at too steep an angle during re-entry and bounced off the thin upper atmosphere like a stone skipping across water, overshooting his intended landing zone by nearly 45 miles before he managed to recover and bring the aircraft home. And the danger wasn't always survivable. On November 15, 1967, Air Force test pilot Michael J. Adams was killed when his X-15 broke up during a hypersonic spin, the single fatality of the entire program, and a sobering reminder that every one of these flights, celebrated or ignored, was a genuine act of courage against genuinely lethal odds. For 35 years, that inequity just sat there, unresolved, mostly forgotten outside of aerospace history circles. Then, on August 23, 2005, NASA finally held a ceremony at what was then called Dryden Flight Research Center at Edwards Air Force Base, and awarded civilian astronaut wings to Bill Dana in person, and to the families of Joe Walker and Jack McKay, both of whom had already passed away. 35 years after their final flights, the record was finally set straight, even though 2 of the 3 men being honored weren't alive to hear it. Bill Dana's own career, incidentally, is a good illustration of how close America came to having an entirely different kind of spaceplane defining this whole debate. After his X-15 flights, Dana went on to serve as a research pilot for a U.S. Air Force program called the X-20 Dinosaur, a genuinely ambitious project that, on paper, looked like it would beat the space shuttle to orbit by roughly 2 decades. Developed by Boeing starting in 1957, Dinosaur was designed to be boosted into space atop a rocket, glide at hypersonic speeds as fast as Mach 18, and land conventionally on a runway like an airplane, all while doubling as a reconnaissance platform and, depending on which planners you asked, potentially a bomber capable of striking anywhere on the globe. 7 pilots were selected to fly it, including Neil Armstrong, and engineers subjected its proposed heat shield to what's been described as the most exhaustive wind tunnel testing program in the history of flight up to that point. But on December 10, 1963, after the program had already consumed around $410 million, more than $3 billion in today's money, and with construction of the first vehicle barely underway, Defense Secretary Robert McNamara cancelled it outright, largely because military planners could never settle on whether Dinosaur was meant to be a research vehicle or a weapon, and the Air Force couldn't justify the cost of a spaceplane without a clear mission attached to it. Had it flown, Dinosaur likely would have added its own chapter to the Kármán line argument, since it was explicitly designed to skim along the upper atmosphere in a way that blurred the line between flying and orbiting even more directly than the X-15 already did. Instead, it became one of the more expensive footnotes in American aerospace history, its research quietly folded into later re-entry vehicle studies, while men like Bill Dana went on to spend the following decades flying other experimental aircraft for NASA instead. All 199 X-15 flights, every single one, ended the same way, as an unpowered glide down onto Rogers Dry Lake, the vast, flat, sun-baked lakebed at Edwards Air Force Base that functioned as the world's biggest natural runway. 2 of the surviving X-15 aircraft are preserved today, one at the National Air and Space Museum in Washington, D.C., and one at the Air Force Museum in Dayton, Ohio, and the data those flights generated went on to directly shape the engineering behind the Mercury, Gemini, Apollo, and Space Shuttle programs. This strange, half-forgotten rocket plane program essentially invented the practical distinction between flying and spaceflight years before it became a household concept, and it did so while quietly running 2 different sets of rules for who got credit for it. Joe Walker's unofficial altitude record from 1963, 354,200 feet, converts to almost exactly 108 kilometers, and that number sat unchallenged for 41 years until a privately funded rocket plane called Spaceship One finally came along to beat it. Built by Burt Rutan's company Scaled Composites and financed largely by Microsoft co-founder Paul Allen, Spaceship One was designed to win something called the Ansari X Prize, $10 million offered to the first team that could send a piloted, reusable spacecraft to the edge of space twice within 2 weeks, funded by tech entrepreneur Anousheh Ansari. On June 21, 2004, pilot Mike Melville flew Spaceship One to just over 100 kilometers, clearing the FAI's Kármán line by less than 400 feet, becoming the first person to reach space aboard a privately built, privately funded spacecraft, and afterward receiving the first ever civilian commercial astronaut wings handed out by the FAA. The flight itself wasn't clean. During the rocket burn, the vehicle began rolling uncontrollably, completing 29 full rotations before Melville managed to damp it out using the reaction control thrusters, all while still climbing toward space. He got the spacecraft stabilized, deployed a clever reentry system Rutan called feathering, in which the entire tail section folds upward to increase drag and slow the vehicle down automatically without any active piloting required, and glided home safely. 5 days later, on September 29, 2004, Melville flew again, this time reaching 102.9 kilometers, and then on October 4, 2004, exactly 41 years after Joe Walker's record-setting summer, pilot Brian Binney took Spaceship One to a peak altitude of 112 kilometers, officially breaking the X-15's decades-old winged aircraft altitude record and securing Scaled Composites the $10 million prize. Both qualifying flights were released from a carrier aircraft called White Knight at around 47,000 feet before igniting a hybrid rocket motor for around 80 seconds and rocketing upward to nearly Mach 3. The technology and the licensing rights behind Spaceship One went on to become the direct ancestor of Virgin Galactic's Spaceship Two program, the same lineage of vehicle that would eventually carry Richard Branson himself to the edge of space 17 years later. In other words, the machine that finally beat the X-15's altitude record is, quite literally, the grandparent of the spacecraft at the center of the billionaire space race story still to come. To understand why nobody in government ever just sat down and settled this question permanently, you have to go back even further, to a treaty signed in Paris in 1919, years before anyone had flown higher than a few thousand feet, let alone into orbit. That treaty, formerly called the Convention Relating to the Regulation of Aerial Navigation, was the first serious international attempt to answer a deceptively simple question, which is, who owns the sky above your house? The nations that signed it agreed on a principle that still underpins aviation law today, that every state has complete and exclusive sovereignty over the airspace directly above its own territory. In 1944, the Chicago Convention on International Civil Aviation reaffirmed that same principle, and it remains the legal backbone of how commercial air travel works across borders to this day. But both of those treaties were written for airplanes, for a world where up meant a few thousand feet. Neither one drew a ceiling. Neither one said that national sovereignty stops being valid at such and such an altitude. That question didn't become urgent until October 4, 1957, when the Soviet Union launched Sputnik 1 from the Tyuratam launch site in what is now Kazakhstan. Sputnik was a strikingly modest object by today's standards, a polished aluminum sphere about 58 centimeters across, weighing roughly 83.5 kilograms, carrying nothing but a radio transmitter that emitted a simple, steady beeping signal amateur radio operators around the world could pick up on their own equipment. It settled into an elliptical orbit with a low point of around 215 kilometers and a high point of around 939 kilometers, circling the planet once every 96 minutes at somewhere around 29,000 kilometers per hour. It made 1,440 orbits before atmospheric drag finally dragged it down to around 150 kilometers, at which point it could no longer sustain its speed, and it burned up on re-entry on January 4, 1958. Sputnik's beeping was heard as a wake-up call across the United States, triggering what's remembered as the Sputnik crisis, and effectively launching the Cold War space race, a competition that wouldn't culminate until Apollo 11 landed on the Moon in July of 1969. America's answer came less than 4 months later. On January 31, 1958, the United States launched Explorer 1 from Cape Canaveral, Florida, riding a Jupiter C rocket developed under the direction of German-born engineer Wernher von Braun, whose Army team had been racing to catch up ever since Sputnik's launch. Explorer 1 was a modest thing itself, barely 14 kilograms and just over 2 meters long, dwarfed by the payloads that would follow within a few short years. But it carried something Sputnik never had, an actual scientific instrument, a cosmic ray detector built by physicist James Van Allen of the University of Iowa. Looping around Earth on a stretched elliptical path that dipped as low as around 360 kilometers and swung as high as roughly 2,500 kilometers, Explorer 1 sent back Geiger counter readings that, at first, made no sense at all. At low altitude, the sensor behaved exactly as predicted, but as the satellite climbed higher, the readings didn't rise gradually the way anyone expected. They simply vanished, dropping to zero, as though the detector had stopped working entirely. Van Allen and his graduate student George Ludwig eventually worked out what was actually happening. The radiation up there wasn't absent. It was so intense that it had completely overwhelmed and saturated the instrument, hundreds of times stronger than anyone had anticipated. That overwhelmed sensor turned out to be the first evidence of what we now call the Van Allen radiation belts, two vast, donut-shaped bands of charged particles trapped by Earth's own magnetic field, encircling the planet far above any version of the Kármán line, a discovery that reshaped how every subsequent space agency planned crewed missions beyond low orbit. It's a nice detail to sit with. The very first American satellite, launched purely to prove the country could still compete after Sputnik, ended up making a bigger scientific discovery almost by accident, simply because its instrument broke in a way nobody expected. But Sputnik also created an immediate and very awkward legal problem. If every nation controls the airspace above its own territory indefinitely upward, then the Soviet Union had just flown a reconnaissance-capable object directly over the sovereign territory of dozens of countries, including the United States, without asking permission from a single one of them. If that had been ruled illegal, the entire concept of satellite reconnaissance, something both superpowers desperately wanted to pursue, would have been a non-starter from day one. So in 1959, the United Nations established a body called COPUOS, the Committee on the Peaceful Uses of Outer Space, specifically to work through these questions, and by most honest accounts, it never really finished the job. According to researchers who have tracked the negotiations, COPUOS has wrestled with the boundary question continuously since 1966, without reaching a conclusion. During those talks, the Soviet Union repeatedly proposed fixing the line at either 100 or 110 kilometers, while the United States consistently rejected adopting any fixed altitude at all. By 1968, the UN's own Scientific and Technical Subcommittee formally acknowledged that it was, at that point, impossible to precisely define where outer space begins. The compromise the world eventually settled into wasn't really a compromise about altitude at all. It was the Outer Space Treaty of 1967, still the foundational document of international space law today, ratified by 115 countries as of March 2024, including every major spacefaring nation. The treaty declares that outer space is, in its own words, the province of all mankind, free for exploration and use by every country, and that no nation may claim sovereignty over any part of it. It bans weapons of mass destruction in orbit and restricts the use of celestial bodies to peaceful purposes. It is a genuinely remarkable piece of diplomacy for its era, and it still, deliberately, does not say at what altitude airspace ends and outer space begins. The treaty solved the political problem, freedom to operate satellites overhead, without ever solving the physical one. And decades later, that same ambiguity is still sitting there, unresolved, baked directly into the legal architecture of the entire space age. Now let's actually climb up through the atmosphere itself, because understanding what's physically happening at each layer makes it much easier to understand why scientists keep arguing about where to draw a line in the first place. Right at ground level, you're standing in the troposphere, the layer that contains almost everything we think of as weather. It extends up to somewhere between 8 and 18 kilometers depending on your latitude, thinner near the poles, thicker near the equator, and it holds something like 3/4 of the entire mass of the atmosphere, along with nearly all of its water vapor. Every cloud you've ever watched drift by, every raindrop, every thunderstorm, all of it happens inside this one relatively thin layer hugging the planet's surface. As you climb through the troposphere, temperature drops steadily, which is why mountain peaks stay snow-capped even in warm climates. Above that sits the stratosphere, running up to roughly 50 kilometers. This is where commercial jets cruise, partly because the air here is far calmer, without the turbulent convection currents that rough up the ride down in the troposphere. It is also home to the ozone layer, and something genuinely counterintuitive happens here. Instead of continuing to get colder as you climb, the temperature starts rising again, because ozone molecules are busy absorbing incoming ultraviolet radiation from the sun and converting it into heat, the exact same mechanism that protects every living thing on the surface from lethal doses of UV exposure. Keep climbing, and you enter the mesosphere, stretching from around 50 kilometers up to somewhere between 80 and 90 kilometers. Here the trend reverses yet again, and temperature plunges as you rise, with the coldest temperatures found anywhere in Earth's entire atmosphere occurring near the top of this layer, dropping to around -90 degrees Celsius, or roughly -130 degrees Fahrenheit. This is also the layer where most meteors burn up, responsible for pretty much every shooting star anyone has ever wished on, as tiny grains of interplanetary dust slam into gas that is finally dense enough to generate the friction needed to incinerate them completely. Above the mesosphere lies the thermosphere, spanning from around 85 kilometers all the way out to roughly 600 kilometers. Despite the name, and despite the fact that temperatures here technically climb dramatically as the thin remaining molecules absorb intense solar X-ray and ultraviolet radiation, this layer would not actually feel hot to a person, because there are so few molecules present that they cannot meaningfully transfer heat by direct contact the way air does at sea level. The thermosphere also contains the ionosphere, the electrically charged region responsible for reflecting radio waves around the curve of the planet, and it is where the aurora borealis and aurora australis put on their light shows. This is the layer where the International Space Station actually orbits, at an altitude of roughly 400 kilometers, comfortably above every single version of the Kármán line ever proposed. Finally, past 600 kilometers, you drift into the exosphere, a region so sparse that individual atoms can simply escape the planet's gravity altogether, gradually fading out into interplanetary space, somewhere around 10,000 kilometers up, with no sharp outer boundary at all. Most satellites orbit within or just below this outermost layer. Walk back through that whole ladder and you can see the actual problem with picking a single number. The atmosphere is not a wall with a door in it. It is a gradient, a smooth fade from thick to thin to essentially nothing, and every layer has a different defining characteristic, whether that is temperature behavior, chemical composition, or what physically happens to objects passing through it. Any single altitude chosen as the edge is a human decision layered on top of a physical reality that does not actually contain a decision point, which brings us to the most compelling scientific argument for revisiting the whole 100-kilometer standard, made by Harvard-Smithsonian astrophysicist Jonathan McDowell in a 2018 paper. McDowell went back and re-examined von Karman's original reasoning and found that the Kármán line as it was actually originally defined by the man himself, sits somewhere between 70 and 90 kilometers, not at 100, and he proposed 80 kilometers specifically as a more physically defensible boundary. His method was not just theoretical. He looked at the ballistic coefficient of real satellites, essentially a measure of how efficiently drag slows a given object down based on its mass and surface area, and found that for a typical satellite, the effective point at which sustained orbit becomes physically impossible sits close to 80 kilometers, and stays close to 80 kilometers regardless of solar activity or other atmospheric variation, which makes it a far more stable, far more physically grounded number than the FAI's rounded figure. He backed this up with historical orbital data, showing that real satellites have survived multiple close passes, called perigees, at altitudes right around 80 to 90 kilometers. Essentially direct observational proof that objects can still be in orbit, in the meaningful physical sense, at that altitude, and not just at 100 kilometers. McDowell's 80-kilometer figure also happens to line up almost exactly with the mesopause, the highest point of that brutally cold mesosphere layer described a moment ago, giving his proposed boundary a genuine, physically meaningful landmark to sit on, rather than just a nice round number. It lines up with something else too, which is the actual, observed behavior of objects falling back to Earth. When a defunct satellite's orbit finally decays and it starts its final plunge, engineers watch two altitude milestones closely: 120 kilometers, above which an object can still technically sustain a brief circular orbit, and 80 kilometers, below which catastrophic structural breakup becomes essentially inevitable. Lower mass, higher surface area components like solar panels and antennas typically tear away first, somewhere between 90 and 110 kilometers, while the denser main body of a spacecraft often survives intact until it drops below that 80-kilometer mark, where the combined heat and drag finally overwhelm it completely. The physical evidence of what happens when spacecraft actually fall out of orbit lines up remarkably well with McDowell's proposed boundary, and considerably less well with the FAI's traditional 100-kilometer line. This research did not just sit quietly in an academic journal either. The World Air Sports Federation, the FAI's own governing body, issued a public statement acknowledging that recent scientific and technical analysis presents what it called a compelling case for reducing the boundary from 100 kilometers down to 80. 70 years after a rounded-up estimate became gospel, the organization that popularized it publicly admitted the physics points somewhere else. All of this raises an obvious follow-up question. If a spacecraft is going to break apart somewhere around that 80-kilometer mark on the way down, what is actually happening to it physically? Here's something that surprises a lot of people, which is that the popular explanation you've probably heard, that spacecraft burn up from friction with the air, is not really correct. The dominant source of re-entry heat is something called adiabatic compression, the same basic physics behind why a bicycle pump gets warm in your hand as you compress the air inside it. As a returning spacecraft slams into the atmosphere at several kilometers per second, it compresses the air directly in front of it, so violently and so quickly that the gas has no time to expand and cool. That compressed air can reach temperatures around 3,000 degrees Celsius, hot enough to strip electrons off the surrounding air molecules entirely, turning ordinary air into plasma, an electrically charged, glowing sheath that wraps around the entire vehicle. Friction plays a role too, but the compression effect is the larger contributor by far. This discovery traces back to two NASA Ames researchers, H. Julian Allen and Alfred Eggers, who worked out what's now called blunt body theory back in 1951 and 1952. Their insight was almost counterintuitive, which is that a rounded, blunt-nosed vehicle actually survives re-entry better than a sharp, streamlined one. A blunt shape pushes a detached shockwave out ahead of the spacecraft, and that shockwave redirects something like 90% of the heat generated during re-entry into the surrounding air itself, rather than into the vehicle's skin. A pointed nose, by contrast, lets that same superheated shock layer hug tightly against the surface, dumping far more of that heat directly into the spacecraft. Blunt bodies pay a price in extra drag and higher deceleration forces on the crew, but that trade turned out to be far easier to engineer around than the alternative. and it's the entire reason every crewed capsule from Mercury and Apollo through Soyuz has that rounded, almost stubby-looking heat shield instead of a sleek missile nose. That plasma sheath causes one more effect worth knowing about, which is that it temporarily cuts off all radio communication with a returning spacecraft, an effect engineers call the communications blackout, because ionized gas at high enough density simply reflects or absorbs radio signals instead of letting them pass through. For a typical low Earth orbit return, this blackout period runs somewhere around 3 to 5 minutes. For the space shuttle, with its longer, shallower gliding re-entry profile, it stretched to roughly 16 minutes of total silence between the crew and mission control. The heat shields built to survive all of this come in two basic families. Ablative shields, like the Avcoat material used on the Apollo command modules, are designed to sacrifice themselves on purpose, charring and burning away layer by layer, with the escaping gas actually helping to push the hottest plasma further from the spacecraft's surface, at the cost of the shield being usable exactly once. The space shuttle instead used reusable insulating tiles, made from silica glass fibers that were roughly 94% empty air by volume, remarkably light for their size, yet able to withstand surface temperatures up to about 1650 degrees Celsius, or 3000 degrees Fahrenheit, while the aluminum structure just beneath them stayed close to room temperature the entire time. For comparison, aluminum itself melts at around 660 degrees Celsius, so those tiles were routinely holding back heat nearly 3 times hotter than the melting point of the metal skin they were protecting. Since we're already busting one popular misconception about spaceflight, here's a second one worth clearing up, because it comes up constantly in the same breath as talk of the Kármán line. Weightlessness has almost nothing to do with actually leaving Earth's gravity behind. Even at the altitude of the International Space Station, roughly 400 kilometers up, Earth's gravitational pull is still around 90% as strong as it is standing on the ground. Astronauts aboard the station float, not because gravity has switched off, but because both the station and everyone inside it are in a continuous state of free fall, constantly falling toward Earth, while also moving forward fast enough sideways that the curve of their fall matches the curve of the planet itself, so they perpetually miss the ground. It's the exact same physics that produces a few seconds of weightlessness at the top of a roller coaster hill, just sustained indefinitely by orbital velocity instead of ending after a couple of seconds. You can actually experience genuine, textbook weightlessness without going anywhere near space at all, using aircraft nicknamed the Vomit Comet, first proposed by German aerospace engineers Fritz and Heinz Haber back in 1950. These specially modified planes, operated at various points by NASA and by companies like the Zero Gravity Corporation, fly a repeated parabolic arc, climbing at roughly a 45-degree angle before pushing over and diving back down along a curve engineered to exactly match the natural trajectory of an object in freefall. For about 20 to 30 seconds near the top of each arc, everyone and everything inside the cabin, including the plane itself, is falling at precisely the same rate, which cancels out the sensation of weight entirely, and passengers can float, flip, and tumble through the cabin exactly as an astronaut would. A typical flight repeats that maneuver 30 or 40 times in a row, adding up to somewhere around 10 minutes of cumulative weightlessness, which conveniently happens to be roughly comparable to the total weightless window Branson's and Bezos's passengers each got on their brief trips past the Kármán line, minus the rocket, the multi-million-dollar ticket, and the argument about which line actually counted. It's worth pointing out that none of this drama around definitions and boundaries ever really touched the astronauts who fly to orbit, rather than just skimming past the edge of it. When Soviet cosmonaut Yuri Gagarin made history on April 12, 1961, becoming the first human being to orbit the Earth aboard Vostok 1, launched from the Baikonur Cosmodrome, his orbit ranged between a perigee of around 170 kilometers and an apogee of around 327 kilometers, comfortably clearing every version of the Kármán line by a wide margin, with no ambiguity to argue about at all. The same is true of China's modern human spaceflight program. China became the third nation to independently launch a human into space when Yang Liwei flew aboard Shenzhou 5 on October 15, 2003, and today's Chinese astronauts, known internationally by the popular nickname taikonauts, a blend of the Mandarin word for space with the same naught suffix used for astronauts and cosmonauts, routinely fly to China's Tiangong space station in orbits sitting somewhere between 330 and 400 kilometers, again, nowhere near any disputed boundary. The entire argument over 80 versus 100 kilometers has only ever mattered for one specific category of spaceflight: brief, suborbital hops that reach just high enough to technically qualify as leaving the atmosphere before immediately falling back down, which is exactly the category Virgin Galactic and Blue Origin were both selling tickets for in the summer of 2021. All of which sets the stage perfectly for the summer of 2021, when this decades-old, mostly academic disagreement suddenly became a very public, very personal fight between two of the richest men on the planet. Before we get to Branson's own flight, it's worth knowing that Virgin Galactic's road to that moment had already gone through a genuine tragedy, one that makes the eventual 2021 flight land very differently once you know it happened. On October 31, 2014, an earlier Spaceship Two vehicle, named VSS Enterprise, was conducting a routine rocket-powered test flight over the Mojave Desert, its fourth such powered flight, when it suffered a catastrophic in-flight breakup roughly 14 seconds after its hybrid rocket motor ignited. Investigators from the National Transportation Safety Board later determined that co-pilot Michael Alsbury had unlocked the vehicle's feathering system, the same tail-folding re-entry mechanism Spaceship One had pioneered a decade earlier, prematurely, while the craft was still traveling close to the speed of sound, rather than at the higher, thinner air altitude the system was designed for. That early unlock let aerodynamic forces catch the tail booms and tear the spacecraft apart in mid-air. Alsbury, 39 years old, was killed, still strapped into his seat when his body was found in the wreckage. His co-pilot, Peter Siebold, survived what remains, as far as public records show, the only known case of a person surviving an in-flight spacecraft breakup. He was thrown clear of the disintegrating vehicle at roughly 50,000 feet, fell for tens of thousands of feet without a functioning parachute, and only had his emergency chute deploy automatically around 20,000 feet, landing with a broken leg, a broken collarbone, and extensive bruising, but alive. The NTSB's final report placed blame not solely on Alsbury's split-second error, but on Scaled Composites' failure to design adequate safeguards against exactly that kind of human error, along with what investigators called insufficient FAA oversight of the entire test program. Virgin Galactic's entire crewed spaceflight ambitions were effectively grounded for years afterward, while the company redesigned the vehicle. So when Richard Branson finally climbed aboard a Virgin Galactic spacecraft himself, nearly 7 years later, it wasn't simply a publicity stunt timed to beat a rival. It was also the payoff of a program that had already cost one test pilot his life to get to that point. Richard Branson had spent years building Virgin Galactic around a vehicle called Spaceship Two, and on July 11, 2021, its latest version, named VSS Unity, carried Branson himself on a mission designated Unity 22, launching from Spaceport America near Truth or Consequences, New Mexico. Unlike a traditional rocket, VSS Unity does not launch from a pad. It is carried aloft, slung beneath a massive twin-fuselage carrier aircraft called White Knight II, or VMS Eve, and released at high altitude before igniting its own hybrid rocket motor and blasting upward on a ballistic arc. Branson flew with a crew of 6 that day, pilots Dave Mackay and Michael Masucci, and mission specialists Beth Moses, Virgin Galactic's chief astronaut instructor, Colin Bennett, the company's lead operations engineer, and Sirisha Bandla, the company's vice president of government affairs and research operations. Unity reached a peak altitude of 86.1 kilometers, 53.5 miles, or about 282,000 feet. That altitude comfortably cleared the 50-mile American standard, meaning everyone aboard qualified as an astronaut under NASA, FAA, and US Space Force rules at the time. But it fell well short of the FAI's 100-kilometer Kármán line by roughly 14 kilometers, and Branson's chief rival made absolutely sure nobody missed that detail. Blue Origin, Jeff Bezos' own space company, had been publicly, pointedly needling Virgin Galactic over the altitude gap for days leading up to Branson's flight, tweeting that New Shepard was designed to fly above the Kármán line, so none of its astronauts have an asterisk next to their name, adding that for 96% of the world's population, space begins 100 kilometers up, at the internationally recognized Kármán line. It was, in effect, a corporate jab dressed up as a physics lesson. And it worked, because for months afterward, headlines kept circling back to exactly that comparison. Part of the drama was also about timing, and Branson made no secret of it. Once Bezos announced his own flight date, Virgin Galactic rearranged its schedule specifically to fly Branson 9 days ahead of him, an unmistakable, almost gleeful piece of one-upmanship in what reporters were openly calling the billionaire space race. 9 days later, on July 20, 2021, notably the exact anniversary of the Apollo 11 moon landing back in 1969, Jeff Bezos flew aboard Blue Origin's New Shepard rocket, mission designation NS-16, launching from the company's Launch Site 1 near Van Horn, in West Texas. Unlike Branson's piloted spaceplane, New Shepard is a fully automated capsule and booster system, with nobody at the controls. Bezos flew with 3 crewmates: his brother Mark Bezos, an 18-year-old Dutch physics student named Oliver Damon, who joined the crew as a late replacement after the anonymous winner of a $28 million charity auction for the seat dropped out, citing a scheduling conflict, and 82-year-old aviation pioneer Wally Funk, whose seat carried 60 years of unfinished history behind it. Back in 1960, a physician named William Randolph Lovelace, the same doctor who had designed the physical screening tests for NASA's original Mercury 7 astronauts, decided, entirely on his own initiative and without NASA's involvement or approval, to find out whether women could pass those same tests too. He started with a pilot named Geraldine Jerry Cobb, who went through the same brutal battery of X-rays, EKGs, EEGs, gynecological exams, and neurological screenings the Mercury 7 had endured, and not only passed, she scored in the top 2% of all candidates of either gender. Lovelace expanded the program to 24 more women, and by the end of 1961, 13 of them, dubbed the First Lady Astronaut Trainees, or informally the Mercury 13, had cleared the first phase. Wally Funk was one of them. During her testing, she was left floating in a sensory deprivation tank for more than 10 hours, roughly triple what the male candidates were asked to endure, and when regulations blocked her from being issued a standard anti-gravity flight suit, she simply borrowed a girdle from her mother and rode out a 5G centrifuge test in it anyway. Lovelace concluded that Funk and Cobb in particular would have made excellent astronauts. It didn't matter. In 1962, Cobb and fellow trainee Jane Hart testified before a special congressional subcommittee, arguing that qualified women were being shut out of America's space program for no defensible reason. But Mercury astronaut John Glenn told the same hearing, in essence, that flying combat missions and test aircraft was simply a man's job in American society at the time, and the program quietly died. None of the Mercury 13 ever flew to space. Cobb, once profiled by Time magazine as a plausible candidate to become America's first woman in space, spent the following decades flying humanitarian missions over the Amazon instead. So when Wally Funk finally strapped into a real spacecraft on July 20, 2021, 59 years after Congress effectively told her and 12 other qualified women that they didn't belong there, she wasn't just riding along as a novelty guest. She was closing a gap the country had left open since 1962, which is a large part of why writer Mary Robinette Kowal's public comment that day, that Funk was, unlike some others sharing her flight, an unambiguous astronaut, landed the way it did. That single flight simultaneously set records for the oldest person ever to fly to space, and the youngest, in the same crew, on the same day. The capsule, named RSS First Step, reached a peak altitude of 107 kilometers, roughly 66.5 miles, or 351,210 feet, hitting a top speed reported around 2,233 miles per hour along the way. The entire mission lasted just 10 minutes and 10 seconds, crossing the Kármán line at 9:16 in the morning Eastern Time and touching down safely under parachutes about 6 minutes later. In stark contrast to Branson's flight, Bezos's crew had gone decisively past every single version of the boundary, American or international. And Bezos, to his credit, was gracious about it publicly, posting a message congratulating Branson and saying he could not wait to join the club. But the altitude gap had already done its work in the public conversation, and it fed directly into a much bigger, messier question that had been simmering underneath the whole affair, with civilians now regularly buying tickets to brief trips above one boundary or another. Who actually gets to call themselves an astronaut? Here is where the story takes one more sharp turn, because on the very same day Bezos flew, July 20th, 2021, the FAA quietly issued revised rules for its own commercial space astronaut wings program, the honor that, until that point, had simply been awarded to any flight crew who crossed 50 miles on an FAA-licensed vehicle. The new rules tightened things considerably, requiring recipients to actually function as crew members, contributing meaningfully to flight safety or demonstrating activities essential to public safety, not simply riding along as a passenger. And that created an immediate, almost embarrassing wrinkle for Blue Origin specifically, because New Shepard is fully automated. Nobody aboard, including Bezos himself, is actually operating the spacecraft. Under the FAA's own newly tightened definition, it was not obvious that anyone on that flight, even the founder of the company, actually qualified as crew in the meaningful sense the new rules required. Writer and space enthusiast Mary Robinette Kowal captured the underlying tension well in public commentary posted that same day, arguing that what historically made someone an astronaut was never simply crossing an altitude line, it was years of dedicated training and a genuine, mission-driven purpose behind the flight, and she suggested spacefarer as a more honest term for paying tourists, while pointedly making an exception for Wally Funk, whom she called, in her own words, a goddamned astronaut, given the 6 decades Funk had spent waiting for a seat she had earned back in the 1960s. The FAA's commercial space astronaut wings program was eventually cancelled altogether, and the argument never really went away. Nearly 4 years later, on April 14, 2025, Blue Origin flew mission NS-31, and this one was designed from the outset to make a statement. The crew capsule itself was named Riss-Kármán line, and it carried 6 women and nobody else: Lauren Sanchez, a helicopter pilot, former journalist, and Jeff Bezos' fiancée, who organized the flight; pop singer Katy Perry, CBS Mornings co-host Gayle King, former NASA rocket scientist and aerospace entrepreneur Aisha Bowe, bioastronautics researcher and civil rights activist Amanda Nguyen, and film producer Kerry Ann Flynn. The flight reached roughly 107 kilometers, comfortably past the Kármán line, and lasted a little over 10 minutes. It was, by Blue Origin's own count, only the second all-female spaceflight crew in the entire 64-year history of human spaceflight. The first had happened on June 16, 1963, when Soviet cosmonaut Valentina Tereshkova became the first woman in space, flying entirely alone aboard Vostok 6 for 3 days. Even after NS-31, women still represented barely 15% of the roughly 700 people who had ever traveled to space by that point. Public reaction to the flight was sharply divided, with plenty of commentary questioning whether a 10-minute, fully automated hop by television personalities and a pop star was really comparable to Tereshkova's solo orbital mission, or to the Mercury 13 women who trained for spaceflight decades earlier and never got the chance. 3 days after the flight, on April 17, 2025, U.S. Transportation Secretary Sean Duffy weighed in publicly, stating flatly that the NS-31 passengers could not identify as astronauts because they did not meet the FAA's own astronaut criteria. Same debate, new crew, same unresolved question. More than half a decade after a Hungarian physicist's rough calculation first got rounded up to a nicer-looking number, and still no closer to an answer everyone agrees on. So where does that leave us, after all of this? It leaves us with a fact that is genuinely strange to sit with, which is that there is no edge of space. Not really. There is a gradual physical fade from thick atmosphere to thin atmosphere to essentially nothing at all. A fade that different scientists, different governments, and different companies have all drawn a line through at different points, for different reasons, at different times, for the better part of a century. Von Karman calculated 84 kilometers and got remembered for 100. The United States has quietly used 80 kilometers for decades, while the rest of the world uses a rounder, higher number. The physical evidence from decaying satellites and the coldest layer of the atmosphere itself both point back toward that same original, unrounded figure. And in the summer of 2021, two of the richest men alive turned that decades-old scientific ambiguity into a genuine, headline-grabbing rivalry, complete with corporate needling, strategically timed launches, and a government agency scrambling to redefine, in real time, what the word astronaut is even supposed to mean. So where do the two companies at the center of this whole rivalry actually stand today? As it happens, both of them are currently grounded, though for very different reasons. Virgin Galactic retired VSS Unity from commercial service in 2024 after it had completed only about a dozen space flights total, having flown an estimated 23 paying customers, a tiny number for a company founded more than 2 decades earlier, and the vehicle could only carry 4 passengers at a time and needed lengthy maintenance between each flight. Virgin Galactic is now betting its future on a next-generation vehicle called the Delta class, designed to carry 6 passengers instead of 4 and fly far more frequently, with ground testing beginning in 2026 and commercial service targeted to restart later that same year. Ticket prices for a seat, which started at a comparatively modest $200,000 back before 2013, have climbed steadily ever since, reaching $750,000 per seat for the new Delta class. Financially, the company has been bleeding money the entire time, reporting a net loss of $279 million in 2025 alone, against revenue of just $2 million that same year. Blue Origin's New Shepard program, meanwhile, kept flying tourists steadily for years after the Bezos and Branson flights, eventually carrying somewhere around 98 people above the Kármán line across dozens of missions. But on January 30, 2026, Blue Origin announced it was pausing all New Shepard tourist flights for at least 2 years, redirecting the program's resources toward Blue Moon, the company's lunar lander being developed for NASA's Artemis program. In other words, 5 years after 2 billionaires turned a decades-old scientific footnote into a headline-grabbing rivalry, the actual business of selling brief trips across the Kármán line has, for the moment, gone quiet on both sides, even as the argument over where that line truly sits continues without them. While the suborbital side of space tourism has been pausing and restarting, a separate and much less publicly argued over category has been quietly setting its own records: actual orbital tourism, which sidesteps the Kármán line dispute entirely by flying so far beyond it that the debate simply becomes irrelevant. The modern version of this began back in 2001, when American businessman Dennis Tito paid roughly $20 million to fly aboard a Russian Soyuz spacecraft to the International Space Station, becoming the first self-funded private citizen to actually orbit the planet rather than just touch the edge of it. That category stayed a rare, extraordinarily expensive novelty for 2 decades, until September 2021, barely 2 months after Branson and Bezos made their suborbital hops, when billionaire Jared Isaacman funded and flew Inspiration 4, the first all-civilian orbital spaceflight, carrying 4 private citizens aboard a SpaceX Crew Dragon capsule to an altitude of 585 kilometers, deliberately higher than the International Space Station itself. Isaacman went further 3 years later, funding the Polaris Dawn mission in September 2024, which pushed to an altitude of roughly 1,400 kilometers, the highest any human being had flown since the Apollo program left low Earth orbit for the Moon, and which included the first ever spacewalk conducted by a commercial, non-government crew using a spacesuit SpaceX had designed itself. Compared against altitudes like that, the entire 80 versus 100 kilometer argument that consumed Branson and Bezos for most of a news cycle looks almost quaint, a reminder that for genuine orbital spaceflight, the Kármán line was never really a ceiling to strain against in the first place, just a threshold you cross within the first few minutes of a much longer climb. And here's a strange wrinkle in all of it that has nothing to do with treaties or altitude charts. Regardless of which line a given astronaut technically crossed, something remarkably consistent seems to happen to people once they actually look back at Earth from above it, whatever the number on their flight log says. In February 1971, Apollo 14 astronaut Edgar Mitchell was riding home from the Moon when he found himself staring out the capsule window at Earth, a small blue and white sphere hanging in absolute blackness, and he later described the experience as producing what he called an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. He wasn't alone. Apollo 9 astronaut Rusty Schweickart described something similar after circling the planet 151 times over 10 days, writing that his sense of identifying with the whole planet had quietly displaced his sense of identifying with any one particular part of it. In 1987, author and space philosopher Frank White finally gave this recurring reaction a name, calling it the overview effect, and it's since been studied and described by hundreds of astronauts across decades of spaceflight, characterized by a sudden, visceral recognition of the planet's fragility and the sense that the borders and divisions we spend our lives arguing over are, from a few hundred kilometers up, essentially invisible. Mitchell himself was so shaken by the experience that he left NASA and founded an institute dedicated to studying it. It's a genuinely strange bit of symmetry when you think about it. Human beings have spent nearly 70 years arguing furiously over exactly which altitude counts as leaving Earth, drawing and redrawing a line that shifts by 20 kilometers depending on which government or company happens to be measuring it that year. And yet the people who actually go up there, whether they crossed 80 kilometers or 100 or 300, keep coming back, describing more or less the same thing, that from up there, none of those lines, real or imagined, seem to matter at all. Maybe that is the real takeaway here. We like to imagine space as a place with a door, a threshold you cross, a moment where you can look back and say, that is it. That is where Earth ends and the universe begins. But the truth is messier, and honestly more interesting than that. The edge of space is not a place. It is a decision, made and remade by physicists, lawyers, air forces, and now marketing departments. And it has been getting redrawn, quietly, for as long as human beings have been trying to leave the ground. Think about everyone this single, contested number has actually touched. A Hungarian physicist doing rough math on a chalkboard decades before anyone imagined a tourist would ever need the answer. Air Force pilots who got pinned with wings within weeks of landing, and NASA civilians who waited 35 years for the same recognition, 2 of them posthumously. 13 women who passed every test asked of them in 1961 and still weren't allowed to fly, until one of them finally got her seat 60 years later at 82 years old. A cancelled Cold War bomber spaceplane that never got the chance to make its own case. A rocket plane test flight that killed one pilot and, almost impossibly, let his co-pilot survive a fall from 50,000 feet. 2 billionaires who spent 9 days and a great deal of money jockeying over a 14-kilometer gap that most of their passengers experienced as, functionally, the same brief, weightless view of the same blue planet. The number itself has barely moved since a lawyer rounded it up for tidiness around 1960. Everything else around that number, who gets credit, who gets left out, who gets to claim the word astronaut, has kept shifting for 70 years and shows no real sign of settling down now. The next time somebody tells you exactly where space begins, you will know the honest answer, which is that it depends on who you ask, and it always has. If this kind of story, the kind hiding inside a number everybody assumes is settled science, is the sort of thing you want more of, this channel is exactly the place for it. So go ahead and hit subscribe, drop a like before you head out, and we will see you in the next one.